Hey guys, it's Greg. Today I'm going to give you an introduction to the PySpark library MLlib. Now essentially this is Spark's way of doing machine learning in Python, and we need to use this, well, when we need to use Spark, which is when we have a big amount of data. If you'd like to see my other videos on PySpark, go ahead and check that out in the video description, although it's not really necessary. I will be giving a quick warm-up to PySpark, so there's everything you need to know in this video right here. So let's get started. I am on Google Colab. It's really easy if you are, because then all we do is pip install PySpark, and that will take a couple minutes or so because it actually is downloading a lot more than there usually is for libraries. Okay, hopefully you got a successful message there, and I'm just going to paste this in because it's very dry and just hard-coded. From PySpark.sql import Spark session, and then get access to Spark with Spark is equal to a Spark session.builder. These slashes are just so that we can keep moving on to the next line and Python will keep reading it. Spark session.builder.master local, because we're not actually doing it distributed, we're just kind of faking that it's distributed. .app name collab. .config spark.ui.port 4050, and then getter create. It's a bunch of boring stuff, but most importantly, you should see that if we output Spark here, Spark session is in memory, and here's all the details for that. So that's it. That's all you have to do to gain access to Spark, and we can start using it. So I'm going to write df, because we're going to make a data frame. df is equal to spark.read.format. The format is going to be a CSV. We're loading in a CSV, and it will be .load, the name of that CSV, which is housing.csv. Now, we don't have this file as is. I need you to go to the video description and download that zip file that's there, extract and upload housing.csv, and I'm going to do that magically here now. Okay, hopefully you have that file up there. If you had problems with that and couldn't figure it out, drop a comment and I'll try to reply to you as best as I can. So .load housing.csv, and then there's generally two things we want to set to true. Header is equal to true, because the first line of that file is a header, and then infer schema equals true as well, because that's basically saying tell Spark to automatically figure out what the schema or the variable types should be. Okay, so we should have df, and then we can just do df.print schema to show us what Spark thinks is the schema of the dataset, which again, just the variable types of all of the different columns in the file. And it takes a little bit because Spark is really hefty. Pandas would do that a lot faster. But here we go. We have longitude, which is a double, latitude, which is a double, housing median age, which is a double, and so on. We see many different columns. This is basically the California housing dataset. If you're not familiar, each row of the dataset is an area in California. It has longitude and latitude, and then it has a bunch of different aggregate statistics on that area in California. The important one for this dataset is that we have an ocean proximity column, and this we will use on purpose because it is a categorical variable, and so there's some particular stuff with MLlib where you need to be very careful about what you do with categorical variables. Okay, so that's the type of the columns. Everything's a double except we have ocean proximity, which is a string. Now what we can do is a quick df.show and some number, say the first 5 rows. This gives in a nice table format the first 5 rows, and we should see here that yes, this is a string over here saying the ocean proximity. Now let's just do a little bit more with this, because generally I like to have an index column, and this doesn't actually have an index, so we can add that in with from PySpark.sql.functions. We will do an import monotonically increasing ID. So df is equal to df.with column. This is just adding a column to the existent data frame. And so we will specify the name of that column, which is ID, and then a function, which is monotonically increasing ID. And this doesn't really take any parameters. It just does like that. And then I will add one thing here. df is equal to df sub ID, and then plus df dot columns, all of them up until -1. So basically what I said here in this line is just reorder the columns where df is equal to df with id at the front, and then all of those columns, because df.columns is a list of strings, which is the list of these column names right here as strings. And so really I'm just reordering as the id is the first column. df.show, I'll just show 3 for the most part, should show that id is now the first column, and it's a monotonically increasing integer. Okay, some really simple stuff. We can do a df.count, and this is just going to be a quick warm up to PySpark. So all of this stuff, we will be using this data set for the MLlib, but in case you haven't seen PySpark before, or honestly, even if you have, please watch this section just as a warm up to PySpark. It will really help. Okay, an example, we can do aggregate functions. So df.select and then total underscore rooms. So I'm just grabbing the total rooms column, and we can do an aggregate with .ag that column, and we'll specify a dictionary where the keys of that dictionary are column names. We only have one left since we only selected that column. So we'll do total underscore rooms. And then the value of that should be a function that we want to do to that data set when we aggregate it. So something like average, that is a string, but you could pass just the numpy average function and that would work as well. And so it'll aggregate that column. And if we do .show, we don't have to do any numbers here because it should just do the whole thing. We get the whole average of the total rooms column, and it's 2,635 or so. Okay, a slightly more complicated example. We can do a function to every or just a subset of the columns of a data frame. So we'll do from PySpark.sql.functions.import mean. Really, that's the same function as the one they're doing there, but it's explicitly as a function here. And we will do df.select, where we unpack, this star is the unpack here, and we'll do the mean of C for C in df.columns, and then .show. Okay, so basically what this is a list generating the average for each of the column names. So it says mean, which is PySpark's mean function here. If we have the mean of a column name, and then we unpack that, well, this is basically just having a bunch of saying mean of this column name. And so it actually knows to automatically do the average of each of those columns. And if we do that, well, then it is okay with that. It just adds average of that column. The ID is completely irrelevant, but the other ones, it should be correct. So the average longitude, latitude, which is a little bit weird, but housing median age makes a lot of sense. Total rooms, as you see, should be the same value as it is over there. And we have the average for each of these. Note that the average of this string column doesn't really make any sense. PySpark decided to not throw an error on that, and they just have null. By the way, this data set also has missing data, although you can't really see it right now. It does indeed have missing data, and we'll have to deal with that later. Note that right here, it is not having a problem with it either. Since we have that categorical column, we will do that for the group by. So we'll do df.group by the same ocean proximity. So group by that column name right there. And so then each of those values with the same ocean proximity, all these near bays and all of the other ones, as long as they have the same value, they will be in a particular group. And so ocean proximity dot ag. Okay, so we grouped by the ocean proximity, and how we'll aggregate it is with this dictionary. And if we do call and then colon average for call in, we'll just do df.columns sub 3, because we're going to do 0, 1, 2, 3. Start at 3, take the average of each of these columns. That's not the very last one here as well. So we'll do that up until -1, so not the end. And then close our dictionary, close our aggregate, and then .show. If we do just .show however many it decides to here, well, it's actually all of them, because there's only 5 different values of the ocean proximity. So there's only 5 different groups. Here's the average of each of those individual variates when we have those individual groups from the ocean proximity. Okay, so very good. Just a review on group by. And one last thing we're going to do before we move on to the actual MLlib introduction is a quick UDF, a user-defined function in PySpark. So for this, you have to specify the type of your return value. And so from PySpark.sql.types, we'll import float type because we're going to make a UDF that returns a float. And from PySpark.sql.functions, we'll import UDF so that we can register one. So the simplest one that we can do is just say define, say, squared. That will take an individual value. And so say it takes, like, you can picture it taking, like, say, this value here or this value here. And so if it takes a value, we will just return, say, that value times that value. It's just squaring it. And then we can make a UDF by doing squared UDF is equal to UDF. It's basically just wrapping this function in this UDF thing. UDF of squared, we pass the function itself, not calling the function, just the function itself. And then the type that that function will return, which is a float type. And you do put the bracket in this case. Okay, so we registered this function as a UDF, and now we can use it like it's a function. So we'll do df.with column. Again, that's just going to add this column to the existing data frame, and total rooms squared. Well, it doesn't actually, by the way, this doesn't actually add it to it unless you set df is equal to df.with column. So I'm just going to show the result of it. Total rooms squared. And so that's the name of a column I'm going to create with squared UDF on a column name, which will say total rooms. Okay, so squared total rooms squared is the squared UDF of total rooms. And we'll do a dot show of, say, 5 of those. Okay, it's going to run that, apply the squared to each of those total rooms values, and it puts that column at the very end by default. And so that's that value squared each time. Whatever that total rooms value was over here, we just have the result of that times itself. Okay, so that is the end of our warm up to PySpark. Just a good warm up to get used to the program. Okay, so MLlib. Well, we have this data frame, which is df. I'll just do again a show to see what we have remaining of that. An ID, longitude, latitude, many columns there, and an ocean proximity. As is with the Kaggle challenge of predicting the median house value, we are going to make a model that does that. Now we are going to separate the data frame into train and test randomly. So one is going to train the model, the other will test the model. If you've seen many advanced machine learning tutorials, you'll know you should have like a cross validation or a validation set. We're just going to do train on one and test on the other. That's it. So we'll do train and test is equal to df.random split, which you can probably guess what that's doing. Randomly splits by the rows, and we'll give it the proportions so that 0.7 or 70% of the rows goes to the train and 30% goes to the test. You can do anything you want as long as those add up to 1 there. And so train and test, well, again, it's not going to output like it would pandas because this is distributed. You can't really see exactly what it's doing unless you explicitly ask for it. Now, always in machine learning, there's a fundamental difference between categorical features and numerical or continuous features. Especially in PySpark, there's a big difference here because one, as we'll see, their imputer doesn't really have a good way of dealing with categorical variables, and imputer being something that deals with missing values. So first, we are going to get a list of column names that are our continuous variables. So we can first deal with the continuous variable stuff and then deal with the categorical variable separately. The only categorical variable is this ocean proximity, and our features for training are going to be not the ID column, but the longitude, latitude. All of these columns we will use for training, except we're going to try and predict the median house value. So we're going to use for training, just one more time, longitude, latitude, housing median age, total rooms, total bedrooms, population, households, median income, not median house value, because we are going to try and predict that. And then the categorical variable we'll also use for helping training is the ocean proximity, which will end up converting to a one-hot vector, but not quite yet. Okay, so firstly, I want to get a list of those column names that are numerical, and it's not too bad. We can do it automatically with numerical features list is equal to train.columns, but we need to remove a couple things. I will just copy and paste that in because it's a little boring. numerical features list dot remove the median house value, remove the ID and the ocean proximity, and then we should see that numerical features list is just those list of variables I made sure to say explicitly a moment ago. Now we're going to do the deal with missing values part. And this again will only work with the continuous variables. So we're imputing the continuous variables. Luckily in our data set, our categorical variable is not ever missing, and so we won't have to worry about it. If you do have a categorical variable missing in your data set, you could remove it. You could do your own sort of custom way of dealing with it, but their imputer, as of right now, is not good at dealing with categorical variables. By the way, just a quick, if you want to know how to deal with it, generally dealing with you use the mode value, and so the most occurring value in the column, you could just do that, or you could make a classification model to try and predict the column, but that's not really necessary. Okay, but ignoring that, from PySpark.ml.feature, we'll import the imputer. And imputer is equal to imputer, where we specify that the input calls is equal to the numerical features list. And that makes sense because we're saying our input calls is going to be a list of column names, and that list of column names is just going to be all of those continuous variables. Those are all the ones that we want to try and impute if we have to. And then output calls is also equal to numerical features list. Because basically what this would be doing in a moment is adding columns to the data frame, except we're happy with just totally overwriting them because we're just imputing the values. So that makes sense to overwrite the column names. Okay, imputer is now equal to imputer.fit with train. So we fit that imputer. Don't really worry about what it's doing, although it's probably just the mean imputation by default. Train is equal to imputer.transform the train. We've now overwritten the training data frame to have the imputed values put in. And then we'll do test is equal to imputer.transform the test. Not too bad at all. And then just to show a couple from train, it really won't look all that different. But as you can see here, there's no errors. And sorry, I meant to put 3 there so that we only see 3 results. There's no errors. It's totally happy with what happened. And there we go. I don't think there should be a problem with running it twice. Whatever. I'm sure it's fine. Okay. If something weird happens, you might have to just restart it because sometimes when you're doing machine learning stuff in Jupyter notebooks, you have a problem with doing stuff multiple times and you get weird errors and you don't know why. Just run it all again if you ever have problems like that. Okay, so how PySpark works for machine learning is that it doesn't really work with these columns here. It doesn't like it being in multiple columns. What we want is to take these and put it all into one column as a vector. So you can kind of picture taking all of this stuff in a row and then just adding another column with all of that stuff packed in to a vector or a list of values in that one column. And you'll see it look like that very shortly. And we make these vectors usually with this vector assembler thing. So from PySpark.ml.feature, import vector assembler. And for this part, I'm only going to grab the numerical ones and again, leave that categorical variable for later. We're going to grab all the numerical ones and put them in a vector. And then after we'll join that vector with another vector from the categorical one to merge together, but we'll see that soon. So numerical, or the continuous ones, numerical vector assembler is equal to a vector assembler where we specify that the input calls is a list of columns that we are inputting to make up that vector. And that's going to be, well, the same list that we already have, numerical features list, those list of numerical or continuous columns. And then output call, just the one, is going to be equal to the numerical feature vector. Okay, and like before, there's just no fit here. Train is equal to numerical, actually I'll just start copying that, numerical vector assembler dot transform the train. So we modify that data set to make a new output column named numerical feature vector. We'll do that for the same for test. So that thing dot transform test. And I'll just show you, say, two rows of train. And so what that does is keeps all of that stuff from before, except we're not really going to use that in part of the training. We're just using this numerical feature vector, which is nothing more than those values shoved into a particular data set or data type and column in PySpark. So now just to show you, since it kind of gives a ... here, I would like to show you a zoom in on what it actually is, although you could probably guess. Train.select numerical feature vector. So grab that column and then .take 2 of those, for example. So this is 2 of these vectors. Just grab that column and then got those 2 vectors. So the first one, again, just all of those values in a vector. And the second one, again, just all the values for that vector as well. Okay, something else we normally do when working with continuous values for machine learning is we standardize or do some sort of pre-processing function to those variables to get them in the same sort of range and style. So I'm just going to do the standard scaler as it's standard. And so from PySpark.ml.feature, we'll import standard scaler. We will make a scaler equal to the standard scaler with input call, just 1, because we're just going to pass it the feature vector we've already constructed. So input call with numerical feature vector. That's the name of that vector column we specified. So only do the standardization on that vector. If you did want to do a different pre-processing to each of the variables, you would have to do that individually and it would take a little bit longer. But we're just going to do standardization or standard scaler to all of those variables. Output call, again, is the name of that column that you want to get produced from that. We could overwrite it, but I'm happy with just making another one. So scaled numerical feature vector. Okay, so that new column there. And then by default, I forget which one of these is true and false, but we want with standard deviation is equal to true and with mean is equal to true as well, so that we just do the normal standard scalar formula, which is take the values, calculate their mean, which is this, calculate their standard deviation, and then we take those values one by one and subtract off the mean and divide the standard deviation, so they all follow roughly a standard normal distribution. If you did want to do a different pre-processing to each of the columns, like some sort of formula for each of the ones individually, that would be a little bit more work, and I'm not going to show that, but you could probably find some hacky way to do that if you wanted to. Scalar is equal to scalar.fit, because you have to fit that on the training set to memorize the standard deviation and mean, so that we do the same exact formula to both the train and the test. And so we do train is equal to scalar.transform the training data set. So add in that scaled numerical feature vector column to that one, and then do the same thing to test, scalar.transform the test. And I will just again show a couple columns, say 3 columns from the training set. We scroll to the end. Again, it kind of cuts it off for us, and so we are going to select that individually with train.select that column, scaled numerical feature vector, and then we'll just take say 3 of those, and just zooming in on that vector that we created, there are all the values. You can see that they're roughly in the same sort of range, and so our standardization was proper. So that's a lot. That's all we have to do with the continuous variable sort of side there. Now we have to do probably about the same amount of work, but different things for the categorical variable. Now, since it starts as a string, which is very typical for categories, it could have already started in like 0, 1, or 2, indicating different categories, but we have different strings. And so we start with a string indexer. So we'll do from PySpark.ml.feature, we'll import a string indexer, which is just going to take each of the strings and map them to a particular column index number. So it'll take near bay and an hour from bay and all those different categories and convert them to say 0, 1, 2, 3, 4, different numbers indicating a column or a category. So indexer is equal to a string indexer. Hopefully you're sort of seeing the kind of pattern they have created here by now. Input call is equal to, well, the column we have in strings is ocean proximity, and the output call is equal to ocean category index. That's just the name of the column we create. We do probably want to keep this column or you really want to keep the ocean proximity column. Otherwise, you're going to lose access to the actual column it's mapping to. So we want that. But what it's actually using for training is mostly this. We'll make this in one hot variable afterwards. But here we go. We have the indexer. Again, we'll do an indexer is equal to indexer.fit. We'll fit it with train. So that learns the mapping. Then we'll apply that mapping with train is equal to indexer.transform train. And then test is equal to indexer.transform test. And we'll do a train.show 3. And all that does is maps those to a particular index. And so we can see at the end here, they're floating values, which is the weirdest thing to me that they made them floats, because I feel like the whole point is they should be integers, but for whatever reason, they're floats. But luckily, they actually are all just individual floats like 1.0, 2.0. We can see this if we do train.select with the ocean category index. And then we'll do a collect, which is something you in general in PySpark or Spark don't want to do, because that grabs all the stuff from the distribution of the computers and it brings it on to this driver node. If you don't really know what that means, don't worry about it, other than the fact that it's kind of bad practice to use that function if you have a lot of data. And so we turn that into a set so that we can see all the different categories that we created, our 0.0, 1.0, blah, blah, blah. There's 5 different categories that we created. Machine learning algorithms do not really like this in this format, unless it was particularly in ordinal, like it should be that 0 and then 1 and then 2, as there's some sort of low, medium, high ordering. Even then, it's still a little bit weird to use ordinal most of the time. And so we want to do in a one-hot encoding. So we'll do from PySpark.ml.feature, import a one-hot encoder. And you should really have a feel of how this is going to work. One hot encoder is equal to a one hot encoder with input call. So just this one column, which we created above. So it should be that column there. And then output call is equal to ocean category one hot. So that's just the name of that column that it's turning into the one hot. Again, I could overwrite that, but probably not a good idea. I'd rather just keep it. One hot encoder is equal to one hot encoder dot fit on the train. And as you probably guessed exactly, train is equal to one hot encoder dot transform the train, and test is equal to one hot encoder dot transform on the test. And we'll do just a quick train.show, say 3 values, 3 rows of that. And at the very end here, we added one more column, which is, it's not a one hot vector. And this confused me a lot when I saw this. I thought I did something wrong. This is actually completely correct, even though it's literally for the list of 3 and the list of 1, which is not a one hot vector. A one hot vector should be, say, zeros all except for 1, where 1 is that index where the category actually is that category. But it turns out that this is for a couple particular reasons. This is PySpark's default of what is kind of a fake one hot vector. It's implementing it in a numerically better way, but showing it much worse for us right now. I'm not going to get into the details as to why it's like that. You can read about it if you'd like. But most importantly, it is proper. Now what we need to do is basically combine our one hot vector, which is our categorical stuff, with our numerical feature vector. So we will concatenate those together with a new assembler is equal to a vector assembler. But this time it's actually taking vector columns, but it really doesn't matter. So we specify that input calls are going to be, it's a list of column names where we're concatenating stuff together. It'll be the scaled numerical feature vector with the ocean category one hot. So that vector we just created before. we want just one output call. Output call is equal to final feature vector. Okay, it's that final vector that for each of the rows, we just have that one vector that we want to pass representing the input for that model. Okay, so input and output are that. And then we can do as before, train is equal to this assembler dot transform the train, and test is equal to assembler dot transform the test. Sorry, I didn't mean to run that, but that's fine. Train dot show with 2, and then we're showing just the 2 rows there, 2 top rows, which we can see here our final feature vector is again cut off. I'm just going to copy this because I'm getting a little bit impatient for the pre-processing. It's so much, like it takes a lot to really pre-process this stuff properly. Train.select final feature vector dot take 2. There, this is the first row, second row of that feature vector. This is what we're passing into the model representing the first row, and this is the one representing the second row. We are finally done our pre-processing, and you could do whatever steps you wanted here to try and train a model. I am going to make it really easy and just train one linear regression model and show you how to get its metrics. So we will do from PySpark.ml.regression. If you were doing classification, this would be classification instead, and then import linear regression. You wouldn't do linear regression if you were doing classification. You would do logistic regression, for example, or like a random forest. We'll do LR for a linear regression. LR is equal to the linear regression, where the style is similar to above with slightly different column names, or parameter names, sorry. Features call, so the column representing our features vector, that is equal to final feature vector. And then what are we trying to predict? That is labeled in label call. What's the column we're trying to predict? It is median house value, which we did not do anything to above. Depending on what you're doing, you may want to scale it or do some sort of transformation to the output as well, but usually just leaving it as is fine, as long as it's the right data set or data type. If we output LR, you won't really see anything interesting. If you did a random forest, then you would see like how many trees it had. You could do any sort of model training you want here, and it's not much different. I don't want to show you the whole process. I've had to train a support vector machine versus a random forest and all that different stuff. It looks exactly like this, just with different imports and specifying different parameters that you'd want. Now that didn't actually do any sort of training. This itself, although we specified the column names here, we actually had no pass here to the data itself. This didn't take the data frame, so we must have to do something like a fit. So LR is equal to LR.fit on the train. That's all you have to do. And if we output LR, well, it's not really going to show you anything interesting. If you instead did some sort of a random forest or other model up here, you could specify the other parameters that you wanted in here, number of trees for gradient boosting, number of trees or steps that it's taking to do that. You could specify all of that and do any sort of tweaking that you wanted. I'm just doing linear regression. It doesn't output anything interesting. There's nothing interesting we have to do with it. And then we could get its predictions. So prediction train data frame, a new data frame, is equal to lr.transform. So the linear regression model itself can transform now that it's fit. It's going to transform that training data set. This, as we saw above with the other style, that creates a new data frame with some modification, some new column probably to it. What it actually did here is make this returns a data frame with the same as train, but it adds a prediction column. It adds the prediction for each of the rows. And it says that in a column name called prediction, but I'm going to immediately overwrite this with the name of that with column renamed, just renaming that column. The column is named prediction, and I'm going to rename it predicted median house value. Okay, so all I did was just overwrite the prediction column name, and now we can do prediction train df.show 5. We should see now that we have the predicted median house value given that linear regression is over here. This is our prediction, and way over there is the actual value. I definitely don't like that they're so far apart. It is extremely weird that way. and so I want to move them towards each other. And we'll do that very shortly once we do the regression metrics, but I'm going to leave that for now. I'm just going to copy and paste this in because it's really the same thing for test, but a little long. Prediction test data frame is lr.transform test, dot with column renamed, same thing as before. And just to show you that, most importantly, as we actually want for a machine learning model, we have a training and test data frame, and we can get the predicted value for both of those. Okay, so now that we have that, generally you want to do any sort of evaluation that you can. Sometimes you could do graphing. It's a little bit weird graphing in Spark because it's distributed, and creating a visual from that requires all the data and like literally showing you all the data. So it's not really well fit for Spark, but you can look up tutorials online if you want to see stuff they do around that. I don't want to show you it though. If you wanted at this stage, you could actually convert this to pandas because most of the heavy lifting in Spark has been done already. And so we could do prediction test pandas data frame is equal to, very simply, prediction test df dot to pandas, and then magically it's a pandas data frame. And so if we do pred test underscore pd underscore df dot head 2, because it's head now because it's a pandas data frame, that's just going to show you the first 2 rows of that as a pandas data frame, and it's going to look exactly the same. And you could do whatever you wanted in pandas now. I'm not going to show you that because, well, that would be another pandas tutorial. If you wanted to do that, go for it. But we're going to keep doing the evaluation and checking in PySpark itself. And so what it needs for this to evaluate the model, it needs one column where it has tuples of the prediction and the actual in that order. It does matter which is the prediction and which is the actual. So if we do predictions and actuals, which is from the test, I'm not going to put it in the variable name, but it's for test. Predictions and actuals is equal to pred underscore test underscore df sub, just grabbing the 2 columns, predicted median house value. Those are our predictions. And sorry, not there. And then median house value is our actual value. And so we can use those together to evaluate the model. To the best of my knowledge, we actually do have to convert it to an RDD. And so predictions and actuals RDD is equal to, all you have to do is take that variable and then take .rdd because it has that underneath anyway. And then predictions and actuals underscore RDD dot take. It is now take instead of show because it's an RDD. We'll take 2 of those and we'll just see that we have, each of them are a row where we have the median, predicted median house value and the actual median house value. So now that we have the whole data set in an RDD where we have the predicted and the actual value, we are just going to quickly convert that to a tuple, and I will copy and paste this because it's kind of boring. Predictions and actuals RDD is predictions and actuals RDD.map tuple. We're just making them tuples, and so if we were to take 2, then it looks exactly the same here, but we got rid of that row thing. It's just tuples, and we know what they are underneath. Now the metrics is very similar for classification and regression, but again, this will be showing it for regression. From PySpark.MLlib.evaluation, we'll import regression metrics, and then we just get a bunch of metrics with metrics is equal to regression metrics on predictions and actuals RDD, and it got all the metrics. That's it. You could of course do whatever you wanted by yourself to get any sort of function you wanted from it, but it just gets a bunch of the well-known ones. And so I'm going to copy this in because it's really big. I'm just getting a string, is equal to this the doc string thing, but it's just a long string. It's equal to the string of mean squared error and curly bracket 0, root mean squared error 1, mean absolute error 2, and the r squared is 3. And then so we dot format because we're passing this into there, this into there. And so it's all stored. All the metrics are stored in just metrics. And so we can get metrics.mean squared error. So I'm putting it with that one, metrics.root mean squared error in that one, and so on. And if we output that, it should have all of our metrics printed out, except it won't because I didn't say print it. If we do print s, and there you go, all pretty, we have all of our metrics. And here, so if you wanted to tinker with the model, you'd say, hey, I'm unhappy with these results. I wanted a lower mean squared error, or I wanted a lower root mean squared error, or mean absolute error, or whatever. Or you don't like the r squared of 0.65, you wanted it to be higher. Then you would go up and you'd change it to a random forest. And I'll give the documentation in the video description, so you can take a look at all of the different models that you can choose from. And you would just play with that, check out your metrics, and move around. If you were doing classification, it would be very, very similar to this. Again, I'll leave the documentation, but it's extremely similar. It would just be classification metrics with making a classification model earlier. And there you go. I hope this was very helpful. This is the end of the tutorial. I hope you got a good feel for Spark ML. It's a great library. It's a little bit clunky and kind of more work than it should be at times, but that's always the case when you need to start distributing data and make it more and more complex. Then the API following will be a little bit more clunky as well, but it's still really good. I really hope this was helpful, and yeah, have a great day, guys. See you later.